Welcome to AP Podcast 13.5C, and we will continue on with this awesome trip on equilibrium. And today, what we're going to do is we're going to look at a very special situation, and that's when we have an equilibrium with a very small k. So, what does that small k mean? Well, if you look right here, okay, it says for a small k, the product concentration is small. Remember, when we're calculating k, it's the products over the reactants, right? How can this number be small? What has to be going on here? For this to be small, that means the amount of products has to be very low, and the amount of reactants has to be high. So what it means is that when you have a reaction, it's not going to be going very far towards the product side. In other words, most of the concentration is going to stay here on the reactant side. So things for us to remember is when we are doing a problem with K being very small, we're choosing X to be small when we set up our ice table. All right? And you will see what I mean in just a second here. But it's going to make these problems very, very easy to manage. So let's look at an example problem here. Okay, we've got this reaction, and look how little is K. And this is something you've got to really focus on whenever you're faced with an equilibrium problem. What is the value of K? Big K tells me it goes forward probably completely. Small k tells me it barely goes. So this is to the -5th, right? That means most of our concentration is going to be over here on this side. Very little of it is going to go there. All right? So it's almost like big arrow this way, small arrow that way. Okay? So look at this problem. Here's our equilibrium expression, how we'd set it up. And we've got our concentration. Notice it's a 0.5 molar because we have a 1 mole solution, but we have a 2-liter container, something we have to worry about, right? Because they're trying to trick us sometimes. It's very nice when they put a 1-liter container, but it doesn't always happen. So I would normally set up an ice chart here. And there you could see exactly what I would do, and hopefully at this point in the game you would do exactly the same thing. And so we've set up these values, 2x squared times x, 0.5 minus 2x. Now, we know that this x is really small. All right, we know that this reaction doesn't go very far to the product side. Most of it stays back here. So what we're going to do to make this problem very easy is we're going to ignore it. We're just going to scratch it out right there. Okay? And now all of a sudden this doesn't become a quadratic equation where you've got to deal with an x cubed, an x squared, an x, that kind of stuff. It's just a nice, easy problem. And so when you work that out, the math, we get a value of 1.0 times 10 to the -2nd. And if you want to check it, definitely go ahead and do it. But it's the way we're going to treat problems when we have a very small x. And how do we know that this is a reasonable way of doing this? Well, we have what's called a 5% rule. And the 5% rule looks like this. If the value of x is less than 5% of the original amount, then our assumption is valid. The nice thing about the AP curricula is they usually don't give you a problem where the 5% rule doesn't apply. If it does apply, then what we would normally do is we would work out a quadratic equation and solve for x that way. But I can tell you right now that that's not part of the AP curricula. But those of you that move on to take college chem or another advanced chem, you will definitely be using a quadratic equation to solve for x. So as an example, if you look right down here, here's the math that's involved in our previous problem. All right, and we get, when we subtract what the x value was, which is 1.0 times 10 to the -2nd, we subtract that from 0.5, we get a value of 0.48 for our starting amount. Well, is that less than 5%? And the answer is yes. If you look at my math here, 0.02 times that, or divided by that times that, we get 4%. So it is a valid way to do this problem. So let's practice one of these problems with a small k and see how it goes. So there's the conditions, all right? And I'm just going to write out the expression here so I can make my ice chart. N2O4 to 2 NO2, right? And originally, I've got one molar, and then look at this volume, okay? So I've got a 0.1 molar. Of course, we have 0 of this. I'll put ice over here. Running out of a little room here, but I think we can finish. The change, what are we going to lose here? We're going to lose x. I hope you would agree with me. Now look at this. We've got a coefficient of 2 there, so we're going to gain 2x, right? And then at equilibrium, we have a situation where it's 0.1 minus x, and we have 2x, all right? Now, if I write my k equals 4.0 times 10 to the negative 7th, and that equals the concentration of 2x squared, right, over 1.0. Oops, sorry, let me do that again. 0. Oh, darn eraser. Okay. Of 0.1 minus x. Now, here's the nice little bonus that we have. We know that k is very small, right? Look how small that k is to the negative 7th. So to make this easy, I'm just going to cross that out. I'm going to solve for x, and I get a value of x equaling 1.0 times 10 to the negative 4th. All right, that's a 4. Okay, and then the idea is, what would my concentrations be at equilibrium? Well, if I subtracted 1.0 times 10 to the minus 4 from that, I get something like 0.999. I mean, it's very small, right? It doesn't change. And then for 2x, I would get 2.0 times 10 to the minus 4th. Now, just to double check, is this value right here, is 2.0 times 10 to the minus 4 5% or less than 0.1? Well, absolutely. And so we know that this is a valid problem. All right, so there we go. A special way to do these with a small k. So let's do another one. If you want, pause the video. I'll write this out and see if you can get this answer. All right, so did you get this answer right here for x? This is 8.25 times 10 to the minus 5th. Okay, and so what that means is those two concentrations are that, right? And then if I were to subtract that value from x, I would get this number up here, 0.099999175. I think you can see that the concentration of that is very close still to 1, which is exactly what we would think, because look at the k value, to the minus 9th. Right, which tells us it's really small. And is this value less than 5% of 1? Absolutely, by a long shot, right? So that's how we treat problems with a small k. Now, just as kind of a summary of what we're going to do for equilibrium problems, and this is right out of your book if you don't want to sit here and write this down, here's our steps. We're going to go ahead and we're going to balance the equation, which makes sense to us, hopefully. We're going to write the equilibrium section. That's absolutely critical, right? Then we're going to list our initial. Now, I want to say something about this, and I might have some teachers or professors that would just absolutely cringe by me saying this. Calculating Q. It is not necessary to calculate Q unless they specifically ask you what would it be before we reached equilibrium. All right, because typically they're going to give us problems where we are going to have to figure it out. We're not going to have to decide whether or not the value would go forward or not forward. So you need to have Q in the back of your mind, but it is not usually critical unless the problem specifically asks for it. Okay, sorry to all you teachers and professors out there that think I'm an idiot for saying that, but hey, that's how I feel. All right, then of course we're going to define the equilibrium concentration. This is all our ice chart, right? And then we'll substitute our stuff, and last but not least, if we have a problem where they want us to find K, we haven't done that yet with these little small amounts, we'll calculate K. So there you have it. Hopefully you're getting really good equilibrium problems. We will definitely practice these in class, and if you have any questions, like always, please ask me next time. See you later.